www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Let's get started then. So today is lecture 8. We'll be talking about density of electronic states. And this is a way of summarizing the band structure information that we had been discussing for last few classes. We have solved the Schrödinger equation and have seen where the electrons sit, and they do not all contribute to conduction equally. Now we are trying to not really remember the whole band structure. That's too much. And rather encapsulate the information in the information about the band gap and the effective masses, sort of how they vary. And this is sort of the third piece of information that again comes from the effective masses. So that is how we are going to summarize the information, and you will see how it works. So we'll talk about calculation of density of electronic states and then give examples. I'll again talk a little bit about characterization of effective masses, putting a magnetic field in and letting the wing electrons swing around a little bit, but this time for a little bit more complicated material, for silicon or germanium, and then I will end. Now you must remember, or you may remember, that when you solve the chronic penny model for one-dimensional solid, we got a solution which stayed between pi over a and minus pi over a, the Brillouin zone, and then there were a series of bands. Now in each band, I pointed out at that time that if you have n number of atoms in that chain, then the total number of state in every band is n, without spin. If you have spin included, then you will have 2n, because each place, 2 electrons, one with up and another down spin can sit. But in general, n atoms, n states. 35 atoms, 35 states for each band. So for example, here if you have 4 bands, then you will have 35 multiplied by 4, 140 states sitting right here. Now, what I want to know in most cases is not the total number, because the total number is not very interesting. Really, what I really need to know is the electrons that move, how many do I have in a given region? So whole band, of course, but remember, when the whole band is all occupied or all empty, it doesn't carry any current anyway. So the one that we are interested in are partially full and partially empty. So in that case, we are interested in a very little sliver of energy band where those electrons sit. And so in that case, we'll have to know how many per unit energy near the bottom of the bands or near the top of the bands. And that is where this density of state will come in very handy. So for example, what we want to calculate many times is how many states are occupied up to a certain energy E, or how many states per unit energy do I have. I'll give you an example, things will become clearer. So this is the density of state. This is an information that you will use often, and for any device analysis that you do. Remember the MOSFET, the bipolar transistor that we'll subsequently discuss, all of them, this is a key quantity to remember. Again, I have a chain of n atoms. A is the spacing. The total length will be L, is n multiplied by A. The solution is given here on the right hand side, and I want to know how many states do I have between K1 and K1 plus delta K. Now here I have just shown you for schematic purposes just 3 states. You realize that these individual states are separated by 2 pi over NA. Now n is 100 million, and so therefore these states are actually very tiny, very closely spaced. I've just shown you 2 or 3 just for representation. This will actually be almost continuous number of states dots on that energy band diagram. Very easy to calculate how many states I have between K1 and K1 plus delta K, or equivalently between E1 and E1 plus delta E, because K and E are related to each other. Therefore, the solution is the same. The same number will come out. So how many states do I have between those two boundaries, E1 and E1 plus delta E? So first of all, I'll have to know what range I'm talking about. So I have a range of delta K, this capital delta K. That's the range of K vectors that I'm interested in. And the points are separated by, well, that's the little delta K. That's how much it is separated by. Now, what is that factor of 2 doing there? It is not spin. What it is, you can see I just considered from 0 to pi over a, the right branch. But of course, I have 0 to minus pi over a, the left branch I also have to consider, because when I'm talking about a given energy range, both the plus and the minus both contribute. So therefore, I'll have to multiply by that factor of 2. Now this delta K, little delta K, I know already 2 pi over Na. So that is how many states I have between for a energy range of delta E, right? That's how many I calculated. So if I wanted to know how many per unit energy, all I have to do is divide by delta K, delta E, the range of energy. And you can see that is exactly what I have done. The Na has flipped over on the top and the 2 have cancelled. I have a pi and delta E over delta K over delta E. So I'm almost done. Somehow, if I can evaluate this delta K over delta E, how the slope changes. Is it going to be different for every band, right? You realize? Because some bands are flatter, some bands have more curvature. So this number is going to be different for every band, and as a result, density of state for every band is going to be a different number. We'll see. So let's continue. I have just copied that same information, state per unit energy. Now remember, Na is L. L is the length of the chain, total length of the chain. And delta E over delta K, how should I evaluate that? Well, you remember that many times near the bottom of the band, I can easily express this curvature information in terms of the effective mass, h square k square divided by 2m star, and that relates E to K, and taking a derivative is no problem. That you can immediately see here. Now, one question for you here. If I couldn't express the EK relationship with an effective mass, how would I have defined the density of state? In this case, this state, how would I have done it? That's the question for you. You should be able to answer that easily. Let's say it's a constant. EK is a constant relationship. How should I have defined it? Anyway, for this particular case, when it's a parabolic density of state, a parabolic band structure, then I have this particular relationship. I insert this dE dk in the first equation. So that gives me an expression that has solely energy in it. Now, if I wanted to know that instead of this sample of L, what is per unit length, how much, per unit length, how many states I have, I'll just divide it by L. You know, the top, the bottom one is just a previous one divided by L per unit length at E. That is density of state. So density of state is number of states I have per unit energy and per unit length. Now, if I have 2 meter material, I'll just take this number multiply by 2. So I'll know the total states, total number of states. If I have 3 EV band energy, I'll just multiply with 3. And that way I will get the density of state information. See? So this is a sort of it's like a density per unit energy per unit length. Then I can manipulate it in any way I want. Now this is a material property. Once I calculate it, this number is not going to change. It's silicon or germanium for a particular band, whatever this number remains as is. and it will not change whether you apply a voltage here or operate the device in one way or other. You see? So therefore, this number will appear as a constant in many of the textbooks and also tables, let's say, or you can calculate it. 1D is fine, right? So you can see how 1D works. Now, how does it behave? We can get a graphical look. So for example, if I wanted to look how does the density of state behave as a function of energy, you can see that it goes as 1 over square root of E. And so starting from the bottom, it will gradually decay away from the bottom. You realize that, right? It's 1 over E. And one thing is, well, you can ask this question that what happens at E equals E naught, right? If E equals E naught, does it blow up? Not really, because remember these states are discrete points. So when you are actually close to E equals 0, you cannot just use this one and assign exactly set it equal to E0, E equals E0, but rather you'll have to calculate the number of states just around that point. Now, what will happen for the density of state for the red curves? Now, there will be a corresponding similarly 1 over E, but this time E going below, and then same for the blue one. And one thing you realize that this shape must be there because, you realize, because the area under the curve, density of state multiplied by the width of this region must be equal to how much? N, right? Remember, N is the total number of states I have. So therefore, if the band is very skinny, my height, the density of state, must be larger than before, right? And you can easily see that where that comes about from this expression. Now, this is something, this 1 over square root of E dependence, you have seen it before. You may not remember. Do you remember that when you have a well, potential well, then the first bound level was at 1, second bound level at 4, third bound level at 9, n squared. So the spacing in one-dimensional solid were gradually getting spaced apart. So when you wanted to do per unit energy density, you realize that as you go up in energy, your density of state will gradually come down. That is the information that is being reflected here. Now, what about two-dimensional density of states? When you have a material like graphene or some other material that is two-dimensional solid, in that case, the spacing, let's say, is A and the other side is B, let's say. This is one of the 5 Bravais lattices, do you remember? A not equal to B and the angle being 90 degrees, for example. Now this I will not do. This is your homework. You should be able to do it yourself, but convince yourself that amazingly, density of state in a two-dimensional solid does not depend on energy at all. That's a very interesting thing. So you should be able to show that as a homework problem. Now let me move on to 3D because that's what is there in the textbook. And many practical devices, your Pentium and various computers, of course, are based on three-dimensional solid. These are sort of material of the future. The 1 dimension and 2 dimension, let's say. 3 dimension is what we often need. Now there is a series of pictures here. Let's go through them one at a time. On the left-hand top side, I have taken a macroscopic cube, meaning the side may be, let's say, 1 millimeter, the length is, let's say, 1 millimeter, the width may be, 2 millimeter, and the height is 3 millimeters, something big. I have taken that. And once I have taken that, I could have constructed the Brillouin zone. How do I construct that? If the lattice spacing is A, then 2 pi over A and pi over minus pi over A. Remember the Brillouin zone? And within each one of them, each solution point will be given by 2 pi over L. That is the little spacing between the points, the dots. It was 2 pi over NA, and remember NA is L, right? The length. And so one side will be 2 pi over L, the other side will be 2 pi over W, and the third side 2 pi over h. And within this little box, little tiny box, there will be one solution sitting in the middle, right? So if you want to calculate how many states you have for a given energy range of delta E, what do you have to do? Well, that is what is being done on the rightmost corner on the bottom. What I have drawn here is two concentric spheres, one with energy E1 and another with energy E1 plus delta E. So you see it's just a shell of a cylinder, right? And we will try to see how many states do I have that I can fit in of those little boxes within that shell of that sphere. That will give me how many states I have per unit energy. Okay, now let's see. This you all definitely know. Let's see whether you can understand this. On the numerator, what I have done is 4 by 3 pi k plus delta k cube. What is that? That is the volume of the red sphere that you can see on the bottom right. And 4 by 3 minus 4 by 3 pi k cube, well, that's the slightly smaller sphere that you have. We have to take it out because we are just interested in the shell of the material. And what is there in the bottom? I have this 8 pi q divided by L, W, and H. What is that? That's the volume of where individual solutions sit, individual points sit. Now, if you compare it with the one-dimensional one, there I had 2 pi over L because it was just 1D. So that's what I had. Then you can see L, W, and H together. We'll call that a volume V. This is the big volume, volume V. And this is a simple algebra. Well, per unit energy, what do? Divide both sides with delta E because that was the range, right? That was the range. And again, you know how to relate K to E. Looks complicated, but this is not rocket science here. And once we have the dE dk for a parabolic band, we are done. It says density of state per unit energy per unit volume now, because it is 3D. 1D per unit length, 2D per unit area, 3D per unit volume. And you can see the V has disappeared, right? Look at the numerator and compare it with the ones that are in the top. Then you will see the V has disappeared because this is per unit volume. So therefore, it's not there anymore. Now again, there is something very interesting here. Do you see? In 1D, the density of state went as 1 over square root of E, right? But in 3D and 2D, it was constant. I didn't show it. You'll do it in the homework. In 3D, it goes as square root of E, increases. And you can plot it out very nicely like this. You can see that how the density of state changes for various bands. Every band has a different density of state because you can see that for band 3, I have effective mass M3. For band 2, I will have an effective mass M2, and therefore the density of states will also be different for different bands. Now, have you seen this before? This square root of E dependence. Have you seen this before? Now, do you remember that I pointed out that when you look at an hydrogen atom and where the energy levels can sit, I mentioned that the difference between 1 and 3D there, that in 1D, they get spaced out as 1 over n squared. But in 3D, they get closer together as 1 over n squared. Do you remember 1 over n squared minus 1 over m squared? That is how we got the energy spacing. So farther out they go out in energy, the energy levels gets closer together. And therefore, density per unit energy, this keeps going up. And that's what is being reflected. Of course, it's not the same thing, but it's a three-dimensional solid. The idea is very similar. That's why it goes up as square root of E. You'll remember this, right? Don't have to, always don't have to derive things. You should be able to remember the formulas almost physically. so that even when you don't have any notes or anything, if you had to write down a bunch of basic calculation, you don't have to always hunt for textbooks or your notes. You should be able to say, okay, physically, what is the content of this material? And you should be able to, at least in graduate level, be able to remember that. What about density of states in specific material? These are the general idea, right? We didn't talk about whether the material we just talked about, whether silicon, germanium, we didn't say that. What about actual material? Well, actual materials sometimes are a little bit more complicated. We will see. The easiest one to think about is gallium arsenide. Do you remember that gallium arsenide, on the right hand side, I have shown the EK diagram, and then there are these two panels which has been pushed together. The panel being gamma to X, which was one panel, and gamma to L being another panel. Now, if you look at the conduction band around gamma 6 point, the blue circle, then you can see that going along the 100 direction, along the X direction, and going along the L direction, the energy comes out about the same, right? And so at a given energy, the amount of delta K you have to travel for that band is about the same, either in the X direction or in the L direction. That says that the constant energy surface for that band is approximately a spherical one. And that is what I have shown on the blue sphere on the slightly left to the figure. And that's the constant energy surface for the conduction band of gallium arsenide. Well, if it is a sphere, then we have just calculated in three-dimensional. A big sphere, inside is a small sphere, and that's the density of state for the conduction band. You see, I have the same formula. Now, one thing I want to point out that you have to be a little careful about, that I have a 2 in the denominator. In the textbook, sometimes you may or may not see the factor 2. Sometimes they include the spin in there already. If they include the spin, the total number of state will be 2 times larger. So that 2 will not be there. That's maybe in many textbooks, but in order to be consistent, I am doing all the calculations without spin. You see? Okay. So conduction band taken care of. You know the conduction band, the effective mass for the electrons. You can put it in there and calculate this number. What about the valence band? Now in the valence band, let's see it a little bit carefully. That's near the gamma 8 point. In the gamma 8 point, you will see that there is actually 2 bands sitting on top of each other. One is called a light hole band. Now, why it is a hole, you know, right? These are almost full, and a few empty spaces, I can take care of those to calculate transport. Now, why is it called light hole, and why is another called a heavy hole band? The reason is that if you have smaller curvature, second derivative of energy with respect to K, effective mass is inversely proportional to the curvature. Shallower the curvature, electrons don't want to go from one place to another, right? So in that case, you can see that the light hole and heavy hole band, they have slightly different curvature, and they have therefore slightly different effective masses. You can again see that this is approximately spherical, and actually one can prove that as well. And correspondingly, the density of state will have the 2 components, one from the heavy hole, another from the light hole. Now, do you see why I have to add them? Because if I am sitting at a constant energy, I could either sit in the heavy hole band or I could sit in the light hole band. Those states are all occupied. It's like chairs here. If you have 2 sets of chairs on this side, both have the same energy. Then some students could sit on the left side, some student could sit on the right side, and when I want to know where you could sit, I will have to add both of them. But assume one set of chairs is significantly higher than the other one, then of course the probability of those states being occupied are not the same. So therefore here I have to add it, not always. Now in some cases you will have to also include the split up band, but that's not necessary here. If you go up in energy or go down in energy, you can see at some point at a constant energy, you not only have light hole, heavy hole, but you also have the split off. So then you have to add 3 pieces together for the density of state. Do you see this? Now, this was good, but these materials that are very useful like germanium and silicon, they turn out to be a little bit more complicated. Do you remember that a constant energy surface for germanium occur along the L direction, and then there are 8 L directions. Do you remember? That's on the corner side. That was from the top of the valence band. That was the easiest point to access, and therefore I have at that point a energy minimum. And how many do I have? I have 8. Not really, because that minimum point is cut by the Brillouin zone in half, and therefore instead of 8 I actually just have 4. 8 halves. That's what I have. How do I calculate here? Now that's a little bit more tricky that we are going to discuss next. It's not sphere, that's the problem, you see. Had it been a sphere, I could take a big sphere, put a little small sphere inside, and I'll be done. I could use that formula. But it's not a sphere, it's a ellipsoid or spheroid. What is it called? Ellipsoid, let's say. And then I'll have to do the same calculation for them. Let's do that. So if I have a ellipsoids like that, then I can always relate the energy E to the wave vector k1, k2, and k3. Now, why am I writing it as k1, k2, k3 rather than kx, ky, kz? This is because that ellipsoid could be oriented in any random direction, you see. Some of them are in L direction, some of them are in X direction. So this is a general form. I write it this way. Now, I also have in the longitudinal side, you see this has 3 axes. In the longitudinal side, I have ml, and on the transverse side, I have the effective mass mt. Now, in general, this doesn't have to be the case. You could have 3 different masses in 3 different directions. For this particular material, germanium and silicon, 2 just happens to be the same. Okay. Now, you see, I could divide E minus EC throughout. Take it to the right hand side and flip the H bar squared from the top to the bottom. Couldn't I do that? That's simple. And I could call this one, this whole thing inside the bracket, alpha squared. It's just a name. And the whole thing on the second and third one as beta squared. So now I have k1 divided by alpha squared, k2 squared divided by beta squared, and the third term. That's the equation, of course, for ellipsoid. That we know, right? So from here, we'll do a trick. We'll say, yes, we could take 2 such ellipsoids and find the skin of it, and then try to see how many states I can put in there. Or I could take this football and squish it and make it a sphere. But you see, the points that I had in the original one, they are sitting there. I'm just squishing it. So essentially, the number of states will not change even when I squish it and make it a sphere, right? Therefore, I can do that trick and very easily calculate this. So the top one in the green and the bottom one in the blue has the same volume. I am defining it so. So they have the same volume. And if I want them to have the same volume, what should I do? You see, for the green one on the top, the volume is 4/3 alpha pi alpha beta squared. You know that, right? If the 2 axes is alpha, beta, and beta, then in general I will have alpha beta squared. If 3 were different, alpha beta gamma, then I will put the 3 alpha beta gamma there. Just 2 happens to be the same. Now the n equivalent is that 6 equivalent values in the Brillouin zone, because we are interested in 6 of them. I'll show you it in a second. Now, if I want to transform them to have the same volume, I will define it as 4 by 3 pi k cubed, right? Definition. So from here, I can easily calculate what the k effective is. Now I can insert the values of alpha and beta in this long expression and define a so-called effective mass on the right-hand side in blue, which sort of represents how the electrons in these states equivalently move, right? I'm just making it an equivalent description. Now this looks complicated, but you can see this E minus EC business in the numerator, lots of h bar squared, they will all disappear, and in the end you will have that little expression over there, that ml, longitudinal effective mass, that you will measure in a few seconds. I will show how it's done. mt, those are measured. As soon as they are measured, I will know the effective mass, and when I know the effective mass, I also know the density of state. Is that right? I also know the density of state right there, because as soon as I know the effective mass, I can put that effective mass in the density of expression. Do you remember? Because now I can use the sphere equation, right? Because I've just transformed it into a sphere. I can convert it and I can calculate it. You remember the 4, right? Half of 8, because the Brillouin zone cut it. Now what about silicon? Silicon is 6. Apart from that, everything else is the same. Why is it 6? Why is it not 3? Why doesn't Brillouin zone just cut it in the middle for this case also? And shouldn't I have 3, right? 6 in direction half cut? Not really. And that is because you'll have to be a little careful. Look at the yellow region that I have marked. The minimum point is really not at the zone boundary. It is a little bit inside, about 20% inside from the Brillouin zone. So actually the constant energy surface starting from the bottom point is wholly within the Brillouin zone for low energy. As the energy gets gradually bigger, what will happen? The part of this football will be cut by the Brillouin zone. As it gets bigger and bigger and bigger, you will see more and more, sort of half is getting cut. You see? Sort of a balloon type thing, gradually getting bigger until it hits the Brillouin zone. And when the Brillouin zone touches it, that part it cuts. And bigger it gets, more part it cuts. And eventually it will become almost like half. But for low energy where we are interested in, it is wholly within the Brillouin zone. And therefore the sort of the football stays in, I have a factor of 6. Now you will have to do a complicated homework. If you don't pay attention to how these things are being done, you'll not be able to do that. But that will clarify all these concepts in one shot. Now finally, I want to talk a little bit about the effective mass. I have already told you about how to measure effective mass by experiment, right, in the last class. But I want to tell you a little bit about how to calculate effective mass or measure effective mass when you have this ellipsoidal type density of state, right? That's something we haven't discussed the previous class. Now very quickly, if you remember, then the measurement of effective mass involves that we apply a microwave frequency about 24 gigahertz, let's say, and then apply a magnetic field. As the electron swings around, then we correspondingly find that at particular magnetic field, there is a sharp absorption when the rotation of the electrons exactly matches that of the microwave signal. Then I have that, and I could calculate from that information. Nu naught is known, the magnetic field of the resonance is known. I could calculate the m star, and that is something I have done before, done in the last class. You can see the electrons also swinging around in the K space. Now this part, some of you have asked questions about that. Why is it when something goes around in real space in circles, why is it in the K space also? You see in the right hand side is a K space. That should it go around the circle also? Right? That's something we should be able to understand. See how it works out. Assume in the real space of x and y, I have an electron the magnetic field is perpendicular to it and the electron is going around, just like that. Now, when the electron is going around, you can see when it is on the top, it has a velocity along the x direction, but it has no velocity in the y direction, right? Tangent on that one. So if you look at the corresponding phase space in kx and ky, you will represent that point in blue by a point on kx, a finite value, and ky equals 0. You see that? Now, when the electron comes here at the green point, then it has only the negative ky velocity, and therefore, when you want to plot it in the phase space, you will plot it here, because that's negative ky and kx equals 0. And I don't have to explain, you can see as the electrons goes around, then on the phase space also, this one will go around. That should have been a little bit up, but this one goes around, and as the electron is going in the real space, the other electron is also going in the k space in the same way. Do you also realize that this must be a constant energy surface? Because h square k square divided by 2m plus h square k y square divided by 2m, that's this. So that's why they go around in constant energy surface, right? Now, another thing very quickly, that when this frequency of going around equals the microwave frequency, at that point you have resonance, right? And another thing, if you wanted to plot at any point what was the ky component, and if it is making an angle of theta, you will say it's ky cosine theta, right? That is the ky, how the projection moves up and down on this particular y-axis. Okay, remember these two things, because this is going to get a little complicated before it gets simplified. So that's why I just mentioned in the real space, this, when it executes a circle in the phase space on a constant energy, it also executes a circle. By the way, these experiments have to be done at very low temperature so that it doesn't get scattered. The electrons, when it wants to finish their orbit, it doesn't get scattered. So these are generally done at liquid helium temperature. These are not easy measurements to make. Now, so these we saw in the last class, that how to make the frequency and how to derive that formula. I just want to go and generalize this on a little bit. I described it in the last class. Please see, if you're not clear, please see in the notes from the last class. Now, I have this germanium, not little spheres on which electrons can go around. Now, let's say I take the sample and put a magnetic field B along a particular direction. How many angles will it make? I have 4 axes, right? 4 body diagonal axes for germanium only. For silicon, how many? I have 3, right? This lateral, perpendicular, and front and back, 3. Here I have 4. So any magnetic field I bring in, it is going to make 4 angles with respect to the 4 axes. And what are those 4 angles? Oh, by the way, so as soon as you put the magnetic field on, the electrons now is going to go around this constant energy surface. That's what I just explained, right? But they are going to go around with different curvature. The red ones has a different angle. They are going to measure the transverse mass, and the blue ones are going to measure the longitudinal mass, and it will be all a mess. And how we'll have to deconvolve it, and I'll show you how. But first, see that there are this sort of 8 equivalent direction, right? 1, 1, 1 direction. You know, you have done this homework before. When have you done it? When you have this 1.10, you know, you apply a force, how many pieces the whole thing can break. They were trying to prepare you for this example, so that you know that there are equivalent of 8 1, 1 n directions, and essentially 4 unique angles with respect to the magnetic field. Okay. Now, I want to prove this formula in next 2 slides, and then we'll be done. This formula is, it looks a little complicated, it's not really. What we'll measure is theta and MC. These will measure, and I'll show you how to measure it. And what we'll get out is the information about MT, the longitudinal and the transverse mass. This is my output. my input is theta and MC. So this is how it works. Now let's think, just generalize the calculation we already did in the last class. That for an electron in the magnetic field in the arbitrary direction, I can always write it in this form. V cross B m dv dt. The right hand side is mass multiplied by the acceleration, right? You know that. And the left hand side is V cross B. Now in last time, it was particularly simple. It was spherical, perpendicular. So I could just make V cross B just a one value. But in general, I should write it this way. Please try it out at home and see whether you agree. Just, write out the Vx as an x, y, and z component and y at bx, by, and bz component. Just write it out. And the m is a diagonal matrix. So one element will be ml, the next diagonal will be mt, the third diagonal will be also mt. So this is a diagonal matrix. Multiply this out 2 minutes. You'll see how this one comes about. Now what you want to do in the next slide is take the second equation for y, and take a derivative once and replace the first derivative on the left hand side by using the other two equations. So that you get one equation for Vy. Again, a 2-minute thing. Just check it out. It's not complicated at all. So now assume that corresponding to an ellipsoid, the angle it makes, the magnetic field, the angle it makes is theta. And so the components of bx, by, and bz are given by that, sine and cosine theta. And this is what I just mentioned. Take the second equation and use the other two equations to find this. And this is an equation for Vy, and the w squared, if you do the derivation, you will see it will come out something like this that I have written over here. Now, what is the solution of that equation? Vy equals a sine omega t. Is that right? Or a cosine omega t. Do you remember 5 minutes ago I said when the electron goes around the orbit, if you take a vertical projection, that it is going to execute as sine omega t going up and down? This is exactly that. So from this is telling you that the electron is actually going around the orbit at that point, and when it's equal to omega naught at that point, it's going to absorb the microwave. So from here, the last step is obvious, you see. All you need to do is in the omega squared, add the resonance condition omega equals omega naught, use the three sets of things, definition, omega naught, omega t, and omega l, put it in the top equation, you get the bottom equation. That's it. Now, it's difficult to explain on a slide, PowerPoint slide, but I really, I'm telling you, it is no more than 5-minute exercise for you. So maybe you want to check it out. Now I am done, because now this is the experimental results I have seen. I have, let's say, magnetic field as a function of absorption in a real material. In this particular case, the magnetic field in 1, 0 plane. So I am specifying what the magnetic field is so that I can calculate the angle with respect to the 3 axes or 4 axes. And you can see those are the electron absorption peaks. So I'll have 3 peaks. I have 3 masses. From the magnetic field, I can use the formula on the right to calculate 3 MCs. And I have 3 angles. What is that all about? Why 3? Why not 4? Because it will turn out that for this particular case, when the field is in 1 z direction, 2 of the angles are exactly the same. So instead of 4, in general you should have 4, but in this particular case you have 3. So how many equations and how many unknowns? Well, you have MC1, MC2, and MC3 from the magnetic field. You have that. And you have theta 1, theta 2, and theta 3 from the angles. So therefore, I have actually 2 unknowns, MT and ML, and 3 equations. So I'm done. From here, I should be able to calculate MT and ML, that I should insert in the effective density of state, and that is how I will get the silicon and the germanium effective masses, right? Density of states. Now, one thing that I leave it as a homework is to prove that why are those, I mean, if you want to know about whole bands, why there should be two valence band peaks. Why should there be two? We just discussed. One is light hole, another is heavy hole. Remember, so they are going to resonate at different times. So therefore, you will have for two holes. And how do you know those are valence band? Well, when you change the angle of the magnetic field, because the valence band is spherical, you see, when you look at a sphere from this angle or from the other angle, it's not going to change. It's going to absorb in the same way. So when you change the angle, the 3 electron peak will move around, because with respect to the ellipsoid, looking from various angles will look different. But the spherical ones will look exactly the same. As a result, that will tell you which one the holes and which are the electrons. So this is how actually people calculate, and that is how check out whether the theory you do, whether those are correct or not. That's it. So we talked about measurement of effective mass and band gaps. That is the information we are going to carry through. Not all this solution of the Schrodinger equation and everything, because as far as we electrical engineers are concerned, for transport properties, conduction band and valence band is all there. That is what we have. For others, there may be other bands. And I am beginning to hopefully convince you that only the fraction of the bands states are important for carrier transport, and that and the states and the number of available states change with energy. That you can see, because effective mass changes, so of course the number of states change, and the density of state captures that information. And this is something is very important. Hopefully you will take a few minutes when you go home and go through this lecture step by step. It's a little complicated lecture, but I assume it's possible to understand for each one of you. You should easily be able to understand this material. Okay, thank you very much.